Hello. In this video I'm going to be showing you how to solve the TJCTF 2020 problem, difficult decryption. This problem should not have been difficult by any means. It's textbook Diffie-Hellman with a fatal flaw. But these problems about Diffie-Hellman are made continually difficult by false information on the internet. False information coming from search results that result in web links that mislabel things and implement algorithms incorrectly. Internet calculators that are usually very reliable, providing incorrect results, and individuals using the wrong terminology to refer to certain parts of algorithms. So, to start, we take the problem description and we go ahead and I paste it into my Python script right here. Now, the original problem description used the letters capital A and capital B, but I've since changed those to lowercase a and lowercase b, such that I'm consistent with the Wikipedia notation and my preferred notation for the private exponent of Alice and Bob, respectively. I'm going to continue using capital A and capital B, except those will mean the result of the modular exponentiation computed by Alice and Bob, respectively. Those results are public and sent over the channel. Then I will use the letter M for modulus. That's not consistent with the usual notation where the modulus is P for a prime. But since the modulus is not going to be prime here, I'm going to use the letter M. Then for the base, as is traditional, I will use the letter G. That G stands for generator, as that base is a generator of a subgroup modulo our modulus M. Now, in this case, the first thing that you want to check for in Diffie-Hellman key exchange is how secure is the discrete log problem pertaining to the exchange. Discrete log is very secure if the modulus is prime. In this case, the modulus is even. It ends in a 6, so it's not prime, and that's going to be a huge flaw. Now, we'll explore that in a minute, because that is ultimately the flaw that allows you to compute the discrete log here and decrypt the message and get the flag. But I also want to talk about another way that Diffie-Hellman could be potentially broken. So that base, G, is 5. And in general, with Diffie-Hellman, we want to choose a base such that it generates a very large subgroup, modulo our modulus M. And if you don't generate a large subgroup, then the key exchange would be significantly less secure and more susceptible to brute force type of attacks. So in order to have a base that generates a large subgroup, it should be what we call a primitive root modulo M. And we'll go ahead and we'll just look at what the requirements are for something to be a primitive root and have that great property for Diffie-Hellman, and how to check for that, or at least sort of check for it at a high level. So this is my paper from a couple years ago, and don't get scared by the denseness of some of the math notation here. We're just going to go over some basic definitions. So for something to be a primitive root mod, or a modulus, in this case we're going to be using the letter A for our potential primitive root, or our base, and the letter N for our modulus. And then the letter K will represent this concept that we call the order of A modulo N. For something to be a primitive root, the value K, the order of A modulo N, must be equal to the Euler-Totient function phi of N. Then it's a primitive root, and it has the property that we want for Diffie-Hellman. In order for this order to even exist, that is for it to be finite, A and N must be relatively prime, and that's here in Theorem 2 and proved below. I'll link this paper in the description if you want to read it in more detail. So we know that these must be relatively prime, and we'll need to check for that in our code. And additionally, we have a definition of our value K here, which stipulates that not only does it satisfy this modular congruence, where A to the K is congruent to 1 modulo N, but it is the smallest value of K, typically the smallest positive value, and I have not stipulated that in this definition here, the smallest positive value of K, for which A to the K is congruent to 1 modulo N. So we'll go ahead and we'll check that phi of N could possibly be the order of our base modulo our modulus, and we're going to check that it's relatively prime first to make sure that it could even be a primitive root, that is, it might have finite order. So in the code, that's fairly straightforward. So we have our factorization of M because it was composite, and I just pulled this from Wolfram Alpha. I'm sure there's a SymPy library command or even just a Python command, or you could have written it yourself because these primes are small and less than 400. But, you know, I used Wolfram. You could also use the Alpratron elliptic curve factorization web app, which is very good for factorizing large integers. That one will solve most things in CTFs if it's meant to be factorized. Then we can compute the totient function. I've written it out manually here just to demonstrate the identity in the code here, which is that for each prime in here, if you have a single instance of it, you just multiply p minus 1 into the final result for the Euler totient. If you have more than one prime, then it becomes p to the alpha, where alpha is the number of those primes that occur, times quantity p minus 1. So here we see that for 3, we have 3 of them, so it's 3 squared times quantity 3 minus 1. And we multiply that all together and we get the totient. I checked it with Wolfram. Again, I'm sure there's a library command, or you could have written an algorithm to take that list and do the same thing, but I just went ahead and wrote it out. So now that we have the Euler totient function, we'll go ahead and run our two checks. The first check is our base relatively prime to our modulus? And yes, because our base is equal to 5, and 5 is not a factor of our modulus. So they're relatively prime, which means the order should be finite, and now let's just check if phi of m could be the order. Not necessarily the smallest k, but we'll check if it's a k such that g to the k, modulo m, is congruent to 1. And when we run our script, it turns out that it indeed is congruent to 1, so we won't have a problem, and it could be a primitive root. So this is likely not a concern, and if we wanted to verify it was a primitive root, we would have to check smaller values. There'd be a little bit more to it, but running the surface level check at least shows that you understand there could be a security flaw here, and that's how to quickly say, oh wow, there is one. This does not prove that there isn't one. So continuing on, the actual flaw is that the modulus is composite, and that's going to allow an algorithm called Pohlig-Hellman to work very, very well at solving the discrete log problem. Now, lots of people get Pohlig-Hellman incorrect in terms of what it is. Looking at the diagram or these high-level descriptions on Wikipedia should explain to you very clearly how it works in general. So at a high level, Pohlig-Hellman does what we call subgroup decomposition in terms of the prime factors of our modulus. So if our modulus is composite or smooth, meaning it has more than 2 divisors and is not prime, then we can break it up into a bunch of prime factors, and we can solve modular congruences for the discrete log problem, mod each of those factors, and then combine the result by Chinese remainder theorem. You'll see that in the diagram right here, where it breaks it up into prime factorization, solves the individuals, combines it by Chinese remainder theorem. In the worst case, where the modulus is prime, the Pohlig-Hellman algorithm will reduce to the baby step giant step algorithm, which is another reasonably okay algorithm, which basically starts at the beginning and starts at the end and kind of like folds it in on itself. It's a space-time trade-off technique, which computes the discrete log faster than straight brute force. Now, I'm not going to go into detail into how these work and go through examples because I've linked things in the description where somebody has done that better than I can currently. I highly recommend you check those out if you want to understand more, but the important bits of terminology are this. To understand that the baby step giant step algorithm is a space-time trade-off approach that doesn't think that cleverly about whether the modulus is composite or not. The Pohlig-Hellman algorithm is not the algorithm to compute the discrete log with a prime modulus. It's the algorithm to compute the discrete log in general. And it works very well when the modulus is not prime. When it is prime, it reduces to the baby step giant step algorithm. Now, this algorithm is implemented by some web calculators. Generally, I like the Alpratron site, but in this case, its discrete log calculator gets the wrong result. And my first thought was maybe it gets the wrong result because we didn't follow the input stipulations here. There's a restriction that says the base in the modulus and the power in the modulus must be relatively prime. But our base is 5 and our modulus doesn't have 5 as a factor, so they're relatively prime. And our power, well, you know, I went ahead and I factored those too in the script. And we could see that they don't share any factors with our modulus. So we didn't violate either condition, but this calculator is getting us the wrong result. What's even more interesting is that the calculator, this is the original value. We could see that this value ends in 5 and is divisible by 5. And it should be pretty easy to prove to yourself on paper that if you have a value a2 times 5 is congruent to 5 to the a modulo m, if you divide by 5 on both sides, which isn't really dividing by 5, it's multiplying by the multiplicative modular inverse of 5 mod m, you'll find that a2 is congruent to 5 to the a minus 1, provided a is greater than 1. Or, you know, if you have a negative number there, then you're going to have a field day finding the inverse of that to convert it to some positive value that makes sense, you know, adding, whatever. In bad notation, a2 is congruent to 5 to the a minus 1, and in many cases that will work. And this result holds true. This number ends in 7776. This one ends in 7775. So the calculator is agreeing with itself in terms of what should happen if you divide out the 5 when you do this discrete log problem. But this result is wrong. And you'll have to, check that yourself with some Python code. And you can easily prove that by, running back the problem and just substitution, see if the result holds. It does not, so you have to use something else. The TJCTF admins on the Discord recommended using this Diffie-Hellman calculator, which does get the result correct, and you'll see the result appears right there, which is different from the result on the Alpratron calculator, which is incorrect. This one's based on Sage, which is Python-based math coding language. Sage is pretty good. If you feel like running Sage to do stuff, it'll work well for you. In this case, I'm going to use the SymPy library from Python 3. So we can see the appropriate SymPy command on this Stack Overflow post right here after we import the discrete log function. And this is going to apply Diffie-Hellman and work okay for us. So we'll go ahead and write that into the Python script. You can see that down here I go ahead, I've already imported the library, and I'm going to use that. And then I'm going to check that it gives me the right result because I now have very little trust for these Diffie-Hellman calculators. Then we compute the secret S as a number, and I check Bob's ability to generate the secret as well. And then I check the in general definition of the secret. And this comes from the overview of the Diffie-Hellman secret generation, which is on this line right here, where our secret, the way that Bob generates it, is Alice's public value to his secret exponent, and the way that Alice generates it is Bob's public value to her secret exponent. So both secret exponents are not sent over the channel, neither is sent over the channel, and the shared secret is equal to this. So we confirm that this is equal to this, and these two agree with each other. Thus we have this big modular congruence, mod M, our modulus in this case. So we have a valid Diffie-Hellman key, then the rest is pretty much straightforward. We undo the XOR cipher and convert it to ASCII, and then we get the flag. I hope you found this video informative and helpful in terms of what words to look for, and I really hope that you go down to the description and look at some of the references and consider learning more about these algorithms from somebody that's qualified to teach it well. Anyhow, if you liked it, please give it a thumbs up. If you didn't, that button is there too, and please consider subscribing for more content.